transfer functions, there were three types. There were 1D transfer functions, 2D, and general higher dimensional. 1D transfer functions are by far the most common. Challenge is that they're difficult to work with sometimes. You have to either work outside in or inside out, sort of thinking of your volume data set kind of like an onion with layers. And it's really a guessing game as to what's the best transfer function for any general volume data set. In general, you can use a histogram to kind of guide you towards the peaks that are interesting, but again, it's very hard to come up with a good, perfect 1D transfer function. 2D gradient magnitude transfer functions are good for medical data sets, especially where you might have boundaries of varying widths, where you can look at the gradient magnitude and use that to classify the boundary effectively. But again, this is tricky because you have to know something about your data and you have to know how to use the transfer function editor. So again, it's challenging. And then you have 3D and higher dimensional range transfer functions, which are, I'd say, still an ongoing research problem. And I pointed you to two papers in the last lecture. But I would say I would be amazed if most people would end up reproducing this, not for the faint of heart. So again, the volume rendering pseudocode. So if any of this ends up in the test or on an exam, I think it would be in a fairly simplistic form like this. And this is more or less what you would need to know. The algorithm is more or less for each sample, P from front to back in the volume. You take the sample of P, and here you're basically calling trilinear interpolation or something like that. And then you have this classify operation, which is really a lookup from whatever transfer function you have. And then you would shade this color using the normal coming from your interpolant. And this is completely optional. If you don't care about lighting, then you can completely ignore that step. And that's volume rendering in a nutshell. And before I leave volume rendering forever, I'm going to mention one last transfer function paper, which is useful for anybody who actually writes a volume renderer and decides that the result is slow and looks horrible. This is a technique called pre-integration that came out of Klaus Engel in 2002, I believe. There's this seminal paper that basically shows you a way of not just classifying individual points, but the interval between points and integrating both this segment between 2 points along the ray and what goes on in transfer function space in the process. And that's really key, because if you look back at the previous lecture slides, the volume rendering integral, there are really two nested integrals in there. One of them is integrating the transfer function, and the other one is integrating the values of the data, the emission or color values themselves. And what this paper, this pre-integration technique is really doing is it's saying, let's actually integrate in between these back and front samples using a lookup table that's sort of pre-integrated everything that can happen between the samples in transfer function space. And the way you do this is a simple 2D lookup table. It's all in the paper, and there's also, if anyone really wants to implement this, I would say ignore the paper and go to the real-time volume graphics book, where they have much cleaner, much better pseudocode. But the paper is there, and so is the book. If you want to use this technique. This is mostly an FYI, just if you ever decide to implement your own volume renderer and you want something that's higher quality. So today we're going to move mostly away from volume rendering, at least from direct volume rendering, and we're going to talk about surfaces and isosurfaces and topology. So especially when we're talking about isosurfaces, these are really a sort of indirect visualization technique. The idea is that we are pre-processing the volume data and we are generating polygonal triangle data from it. So I'll talk about the difference between explicit versus implicit representations. We'll give a few examples of terrain visualization, which are really explicit surfaces. And then we'll talk about contours. Then I'll talk about isosurfaces, marching cubes, the seminal isosurface extraction algorithm. I'll talk about some alternatives like particle extraction, splatting, raycasting and ray tracing isosurfaces. And then lastly, we'll talk about topology. which is really how you simplify large, complicated data into its bare bones mathematical components. So minima, maxima, saddles, how you build data structures out of that and try to learn something about the data from that. Whoops, that was a repeat. So onto surfaces. Yeah, and as mentioned, surfaces are really, when we're talking about isosurfaces, this is the seminal example of indirect visualization, where you're talking about generating geometry as part of some step in the pipeline, and then using rasterization, but really any sort of rendering algorithm to render triangle geometry. So in graphics, this probably is kind of a repeat from something you might have heard when Alex has talked about the difference between SVG and raster graphics in D3. But in broader computer graphics, and definitely when you go to 3D, we often differentiate between explicit and implicit geometry. And usually when we're talking about this in scientific viz or spatial viz, when we talk about explicit geometry, it's geometry that's really defined by the vertex positions. So for example, a triangle mesh. And implicit geometry is something that is defined by some implicit function, some kernel of a kernel filter that's coming from your scalar field. So it's very similar but subtly different from the field versus grid topic, but there's a lot of overlap here. The idea is that an implicit surface comes directly out of your field, and an explicit surface is explicitly defined mesh geometry. So points, vertices, and indices, the type of stuff that you would see really in conventional graphics. And then you have something else. You have parametric geometry, which is explicit geometry in real domain space, interpolated via parametric equations in usually some lower dimensional space. So I think of NURB surfaces, Bezier splines, Bezier patches, and these are really the domain of computer modeling and really coming up with surface forms on vehicles, on aircraft. So this is something that you see a lot in CAGD, and you do see in visualization and in scientific computing, but probably less than you would see standard implicit geometry from scalar fields and from vector fields and from multi-fields. So this is the difference between implicit versus explicit and parametric. And indirect visualization usually involves turning implicit geometry into some explicit geometry, usually to be rasterized, but really to be rendered anyway. So this is just a simple example with a circle. So in the explicit form of this circle, which is actually happens to be a parametric equation because this is 2D and it's an analytical explicit representation. If you wanted to represent this explicitly, it's f of x is r cosine x, r sine x, and you have a coordinate system out of that. And if you want to represent this implicitly, well, this is really just taking the x squared plus y squared plus z squared equals 0 equation. That is more or less your scalar field, so to speak. And to get that in terms of f of x, y, you just take the square root to subtract the radians, like this. So you end up with square root of x squared plus y squared minus r. And this is what we're talking about when we're talking about the kernel of an implicit function. So then we have this question, what if you actually have data points? How do you go from something that might actually be, it might be a set of points to begin with, and how do we turn that into an implicit? Again, this is very similar to the difference between scalar and between raster and vector graphics. You really have two choices. One would be to enumerate a set of points and specify their connectivity. So this would be very much the explicit approach. And I think of the explicit approach as being more kind of the vector graphics approach, where you have points and vertices. And the implicit approach would be, in this sense, more of the raster approach. So there's a subtle difference between the explicit-implicit divide and the scalar slash vector slash raster divide, and the field and grid divide. It generally depends on what data you're starting with and what data you'd like to go to when you actually render it. So again, the advantages of explicit versus implicit. So explicit, so sort of the vector approach, the advantages are that you have piecewise approximation, you can use a set of points in a triangle mesh or a set of polylines in this 2D example. And it's very easy to modify the geometry directly because you don't have to go back and paint on some canvas and convert it from a scalar field to raster graphics, and you don't have to worry about any of that. For the implicit, it seems more complicated because you're dealing with a kernel of implicit function, and the implicit function is the scalar field. Again, in both cases you have piecewise approximation, but you're dealing with pixels or voxels instead of points and vertices and edges. And you have a scalar valued grid, 2D or 3D. But there's some advantages to this. I mean, it's first of all, you have this sort of continuous representation in 3D, even if you only have piecewise approximations based on your reconstruction filter. You have easy inside and outside tests. You can immediately look at, for example, the sign and determine anywhere in the image if you're inside or outside with respect to an ISO value, with respect to a contour. And anytime you have changes in topology, changes in shape, these things tend to happen very, very smoothly. So if you wanted to modify your vertices and edges, you can actually mess up your entire model and change the topology if you don't have everything nicely connected together. Whereas if you change a few values in your scalar field or in your image, then you don't really have any adverse impacts in terms of how your data are connected. So a simple, I guess high fields are maybe not a purely implicit or purely explicit structure, but they're a good example because they're implicit with respect to two dimensions and explicit with respect to the third, the height. So they're an interesting visualization tool. And they also show up a lot in GIS, a lot in visualization. There was a time even when I was a student starting out in graphics and viz, when rendering large height fields was still a problem, and there were not a lot of good solutions for doing that. And now it's something that you just trivially send to your GPU, and you can even render these pretty efficiently in 3.js. So anyway, a height field is really a 2D implicit. It's some f of xy equals h, where h is the height. This can be represented very simply by a raster image, like a grayscale 2D texture. And what you want to do is not just show that 2D texture, but have some way of reconstructing a mesh from it. And you can either do this using explicit geometry by interpolating the mesh, or implicit geometry by ray tracing what are really parametric patches, but you can represent them very easily, like two-dimensional, bilinearly interpolated patches. You can also do something nice and smooth, like a B-spline. You have a lot of options. And these data sets are great because there are a lot of them. Nowadays, they're generated almost in real time from UAV sources, from aerial photography. Before then, actually still now, but it's a little bit less common. UAVs really sort of displaced LiDAR as the main acquisition source for a lot of these geospatial data sets. But you get some great examples. So here's an orthophoto aerial photography data set. And very often you'd look at this from a few different viewpoints and you'd want to reconstruct a digital elevation model, which is your height field. The state of the art in terrain rendering I can think of is this great out-of-core system that folks at University of Munich did back in 2009, and they were doing real-time out-of-core rendering of a 5 terabyte data set with quarter-meter LiDAR resolution. And this is on an old GPU. So this is, I would say, a very specifically well-engineered system for terrain rendering. So this is the kind of result you get from that. And all of these are essentially just linearly interpolated patches. They're not even using bilinear or anything like that. These are a bunch of flat shaded triangles that just happen to look nice because the resolution is so fine in between these points relative to how far you are zoomed out. So this is what it looks like underneath the hood when you have the rendering. And I'd say this is a great example of using the exact same technology you would for games, using standard OpenGL graphics and getting real-time results out of it. Yeah?
So in this scenario, is the vertex density the same overall?
It's not, it's adaptive. So the further you get out, the coarser your mesh is. And that's actually a lot of what they're doing is they're generating a technique that generates, they have a technique that generates a lot of geometry up close and not so much as you get further away. So it's what we, in graphics, we call an LOD technique, or a level of detail technique. And that's what principally made it go very fast, was the fact that using the rasterizer, you have sort of a fixed geometry budget. You can't really afford to send a lot of triangles that far out. You wouldn't necessarily want to, even if you could. And they had a raycast alternative to this on slightly better GPUs than their original approach had. And the ray tracing approach is actually a little bit different. Here you actually don't care about as much about LOD representation because it takes about the same time to ray trace or raycast really, really dense geometry that's far away as it does coarse geometry that's far away. And the other nice thing about raycasting is you can, if you want an analytical ray bilinear patch intersection that makes it look nice and smooth when you're up close, you can get that. I would say for something like the Vorarlberg data set where you really want to see a bunch of trees, seeing a nice smoothed out bilinear patch is probably probably not much help, but hey. What's interesting is that they basically expected that this was going to be slower than the rasterization approach for everything they were doing, but it turns out that it was actually faster for the high resolution data and much slower for smoother low resolution data. And data size doesn't have too much to do with it. It's all really just the characterization of how many rays per pixel and where does it start to make sense to raycast instead of rasterize. So this is, again, a Eurographics 09 short paper. Not the most prestigious journal ever, but, Eurographics is quite good, but I would say it's probably the state-of-the-art of anything that I know. And here are just some more terrain examples. So some collaborators of mine at EVL, so Jason Lee and his group had a real-time terrain visualization system for whole planets that they implemented in the planetarium in Chicago. So I can give you a quick YouTube video of that. And this is all just standard rasterized graphics and explicit geometry, terrain rendering. Really the exact same off-the-shelf technology that you'd use for video game development. Whoops. And you can see it's adaptive. It's very much, even though it's not the same system as what the Munich group did, it's very much the same spirit. And this came out, I want to say, a few years after the Munich group's work. And let's see if I can go back to the 3JS example. Hopefully they did not take this down. So this one was kind of neat. This is a project that was created by the LA Times to explore a DEM scan from satellite over Mars, looking at the Gale crater on Mars. And they actually have a sort of a tutorial on how they did it. This is the DEM and the aerial photography data they were working off of. And they turned this into this relatively relatively easy self-contained example. Most of the code involved in converting this to Three.js was actually the reader for the DEM data, and the actual rendering code in Three.js was pretty straightforward. Let's see if I can find it. There we go. Well, we actually have to wait 10 seconds. I guess we do. So yeah, and this is all just browser-based. Probably it's not going to perform as well as something like the Vorwerk demo, where you have a high-end GPU or several high-end GPUs, and whoops, did I crash it? I think I crashed it. Oh wait, there we go. So yeah, they have a little video site, a little virtual sightseeing tour. So I would say this is the sort of thing that would be nice for a museum exhibit or for sort of web-based outreach, but I don't necessarily see it taking over the height field world by storm. But who knows? In the future, you could actually have sort of a convergence between what you can do through WebGL on your laptop and what you can do on a large interactive workstation or something like that. Let's see if I can go back to the lecture. Here we go. So that more or less wraps up height fields. And now let's talk about contours and isosurfaces. So, quick question, has Alex covered contours yet in any of the InfoViz or DataViz lectures? No, not really? Okay, all right. So this is sort of just a 2D data basic, but a contour at a value v of a scalar field f of xy is the set of curves where f of xy equals v. And there are a few ways you can show contours. Generally, you can choose between a plan view, which is sort of an overhead view, versus a profile view, which is more like the side view you see here. And sometimes they would have just illustrations that link the two. So quick question, why is it best to use multiple contours? Well, it's best to use multiple contours because the alternative is you don't actually see most of your data set. You really need multiple contours to get a sense of where the peaks and the valleys are. That's sort of the whole purpose of contour visualization when you're looking at height fields. And there are lots of different applications. A lot of the time there's strong overlap between visualizing contours and visualizing flow in the context of 2D or meteorology data sets. So Sam Kleinen had a very nice applications paper on this at IEEE InfoViz 2 years ago. I would say straightforward stuff when you look at it. Generally, contours, just looking at the contour itself and color coding them, it gives you a sense of how the scalar field behaves, but not necessarily what up and down are. So you really need some additional context to understand that. But I guess from more of a design standpoint, if you look at 4 different ways of representing a height field like this, and you can see with and without contours. Can anyone describe how the contours help visualize a simple height field like this? Okay, I need a victim. All right, no takers. Well, in short, the contours really show you, actually it's really tough to see with the light on, but you can see this black, can everyone see this black contour?
No, I was going to ask which ones had contours.
Can anyone help me turn off the light right next to me? There we go, that's more like it.
Yeah, that's better.
Oh, okay, that's great. All right, so now can everyone sort of see this black contour?
that just represents one equal height.
It's one ISO value, one value. And it shows the interpolated curve where that value exists in the data set. Note that curve can actually be disconnected. But the basic idea is that by showing this one curve, you can immediately tell that there's a big, huge plane, a big, huge flat region where below this curve, it's basically flat, and above this curve, you start to have hills, you start to have mountainous regions. So what's interesting is that if you looked at a histogram of where these curves were, or you had some sort of analysis structure that said, this is the area of this contour, or the area of all contours represented by this ISO value. All of a sudden, you'd be able to just look at statistics and tell something about the data set that you wouldn't be able to know otherwise. So this is, I think, what makes the contours powerful compared to just a heat map or something like that, where I mean, yeah, there are things you could do if you volume rendered this, or if you had a color map, you can see, oh yeah, look, it's mostly red, but you don't really know where the red is with respect to value. Yeah?
So I was wondering if you're not really concerned with the accuracy, would it be worth it to use these contours instead of height maps? Will the cost of the interpolation be higher if you just use the height map or not?
I mean, it depends on what you want to see, the resolution of your contour and the height map. You'd have to run essentially marching squares on it to generate the contours. And in some cases, it might be faster in practice just to rasterize a 2D image. But I think in 2D, no one really cares about cost or performance. It's just not a problem. In 3D, it gets trickier, and then you actually have to care a little bit about performance. And you know, actually, in a few slides, I'll really talk about 3D, where it just does not make sense to extract a big isosurface, but it does make sense to raycast an isosurface or raycast a volume, or do volume rendering, for example. But yeah, there are pros and cons, there are trade-offs. I'd say performance, at least for 2D, is not the big one, but you get certain things out of having, if not the explicit representation itself, then knowing that you have sort of a spectrum of contours, and contours that are important and other contours that are somehow less important. So this is what a contouring algorithm looks like in practice. In 2D, it's something called marching squares, and it's actually a pretty simple idea. It's really just a process of identifying, starting with a cell, then identifying the grid where the contour would actually cross, so where you have assigned chains with respect to an ISO value. It means that basically one vertex is above, another vertex is below, and then you know you have a crossing. So then you find those crossings, and then you connect those crossings. And then the idea is that once you've done that, you just chain them together and you have a polyline. So it's incredibly easy. And there's a nice little case table you can construct where you have no crossings, a singlet, double adjacent, and double opposite. But this is, again, extremely easy code to write. And the only question, the only problem this really creates is this question of ambiguity. You can have crossings where you're not really sure if the contour should go one way or another. And in fact, it turns out it doesn't really matter which way you choose to create the contours, as long as you choose consistently. So if you choose to always look at the top faces and assume that crossings happen there, then you have to stick with that assumption, or else you're just not going to end up with continuous lines. So this is sort of an example of what happens where you want to resolve this ambiguity, and you don't really know which one is right. It's really a question of which way do you consider to be up in your interpolation. Is almost the way to think of it. So anyway, this is, I'd say this is the easiest way to visualize the ambiguity problem. It gets much more complicated in 3D, and in fact, now that I think about it, the fact that the 3D case took probably almost a decade to actually resolve and resulted in a paper that had 600 citations. Yeah.
So I'm not sure where this ambiguity is coming from. Like, are we talking about like a mountain peak kind of a thing?
It's almost entirely artificial. I mean, when you think about it, the contour is more like a construct that you're coming up with to say the value is so this is where in space this value goes. And it's really more of a question of how you're determining the interpolation, what you think is happening on the inside of the cell with respect to interpolation, as opposed to anything inherent or intrinsic in the data itself. So what's really happening is there's a topological change. So there's a crossing somewhere in the middle of this cell, and you need to determine
The crossing of two contours of the same value.
Yeah.
Okay.
So basically, this happens when you see, and this actually makes sense in the 2D case. You can see we have red on two corners and green in the other corners, and this only happens when you have that situation where you have a sign change really on all corners. Most of the time, you only have a sign change with respect to one, but really what happens is now you have a sign change with respect to two, and you have to pick the vertices that you want to connect. You have to choose how you connect these vertices. So you can either connect them this way, or you can do this. In practice, this is a really bad way because it's sort of, you're not staying consistent. But in the case of marching squares, as long as you pick one or the other, then you're going to be good. Then you'll have continuous curves, and you're not going to have any problems. In 3D, yeah, it gets much trickier. So this is marching squares, 15 cases, and then you have the two ambiguities where you have red and black. Let's go on to 3D. So in 3D, contours are something we refer to as isosurfaces. So you have a scalar field that's 3D, so some f of x, y, z, and you're looking for a value v in the scalar field where you have the set of surfaces where f of x, y, z equals v. And if you specify these, you end up with nice single surfaces that show this contour. If you look at, it's a lot like what we saw in volume rendering, except you're just looking at one discrete surface here, as opposed to sort of a peak in the transfer function. So you can see this is the visible female on the left. This was probably one of the toughest volume data sets to analyze in the 90s, and it probably spawned hundreds, if not thousands, of actual papers related to how do we deal with a data set this size. And in fact, it was probably only in maybe 2007 that people were able to just throw this in a volume renderer and have it all just work on pretty much any piece of hardware. Before then, people would look at subsample versions of this data set or smaller portions of it, and then they would just look at what they could. And over here you have something called marching tetrahedra, which is, well, I'll actually get to that algorithm in a bit, but it's, again, an isosurface. So you have two different ways of rendering isosurfaces here that are completely different. One is pulling isosurfaces out of a tet mesh, and ray tracing isosurfaces from a scalar field. So, at the risk of being a little bit confusing, I'll talk about level sets. You'll hear the term level set a lot when you, actually, show of hands, who's heard the term level set before? Okay, great. So this will be a slightly more hand-wavy definition of level sets than you might hear in a more theory-oriented class, but generally a level set it's a generalization of an isosurface. So given a function f from some higher dimensional real number space to a lower dimension, so really just a R1, the level set is the set of points x such that f of x equals c for some value c. So you can think of c as being the iso value. So in R3, the level set is an isosurface, and more generally we call that a contour. And what's interesting about this value c is that it defines not just the surface itself, this discrete surface, but two other manifolds that we call the superlevel set and the sublevel set. So it defines the sublevel set, which is the set of all points in the data set whose value is less than or equal to C, and the super level set, which is basically all the points that are greater than or equal to C. So it really divides the data set into two submanifolds. So that's maybe a little bit technical, but especially when we move to the topology topic, you'll see how this starts to come into play, especially when we start to talk about contour trees and merge trees. Really, the goal of those are to chop up your data set according to range and analyze them in a specific way that tells you something more than you could just by looking at a rendering. But anyway, let's trying to stay a little bit more on track. Let's look back at how you'd actually isosurface from a 3D grid. So your problem is actually kind of simple. You're given a big 3D block of numbers, so your scalar field in a uniform grid, and we want to make a picture. We talked about volume rendering already, and before volume rendering, people had a concept like slicing and just clip planes and cut planes. And there was a time actually before 1987 when they had approximations to marching cubes that looked really, really horrible, but people thought this was the best you could actually do. And it wasn't a question of computing power, it was that nobody had actually come up with a technique from generating a continuous surface from a 3D volume. And the technique that did this was the 1987 paper Marching Cubes, a high-resolution 3D surface construction algorithm from Lawrence and Klein. And actually this slide is out of date because last I checked it has well over 11,000 citations. So this is one of these papers that just never will die and people will use over and over and over again, even if the whole point in citing the paper is to say I've come up with a better way. But in practice, oh yeah, never mind, yeah, we're almost up to 12,000, and that's last year, so I bet we're over 12,000 now. So the marching cubes algorithm is really close to marching squares. And the only difference is that in marching squares you have 15 cases. Actually, marching cubes you end up having a similar number of cases. It's actually, I think, 15 exactly. And it's just that a lot of the cases are really duplicates of the other. And so if you actually looked at marching squares, I think it would end up being 6, but I'd have to go back and take a look if you looked at all the duplicate cases. So the basic idea of marching cubes is to consider the cell, classify each vertex as inside or out, then build an index, so sort of a hash that goes from your cell to where you put the surface. Get an edge list from this table, then interpolate the edges, again very similar to what we're doing for marching squares. And then because you have a surface, and you actually want to shade it like a surface, you actually kind of care about the gradient, about the normal of the surface at some arbitrary point, or at least at the vertices. So you have some way of computing the gradient of the cell at each vertex. And then, in step 7, you have to deal with the ambiguous cases, which are much more ambiguous and much more challenging in 3D than they were in 2D, but we'll go to that, and then you go on to the next cell. And you have to do this basically for every cell in which there's a crossing. To give you an idea, a typical 1K cube volume data set would be 1 billion cells. So this is a challenging problem when you start to have larger three-dimensional data, because something to the cubed is generally quite big, and you have to come up with clever ways around it to make the problem more tractable. But anyway, this is what it looks like inside one cell. So you start out with your voxel with 8 vertex values like this, and then you classify each voxel according to whether the surface lies, so whether the voxel is outside the surface, so the value is greater than the isosurface, or inside the surface, value is less than the isosurface. So that's your first step. And then you have sort of a binary labeling of each voxel that creates the index for that voxel. So you end up having 8 of those in total, and it's just like this little hash code. And then you end up taking that hash code and mapping it to the case in the marching cubes case table. So in all total, you'd have 256 cases, but because there are a lot of symmetric cases, you end up with 15. And I would say this was the real cleverness of the paper. There was a previous paper that actually came up with more or less the same marching cubes algorithm, but it didn't have this case table where it reduced the 256 cases down to 15, and it also did it for more general blobby graphics data as opposed to medical data, which everyone cared about. So this is the case table itself. This is how you would map from any voxel with any set of crossings into a type of a surface inside, or really a set of triangles inside that voxel. So in this case here you have 8 values above the isosurface, 0 below, 7 above, 1 below. This can get a little bit tedious, but it gives you the idea of what marching cubes is doing. Basically, once you have this, once you have the set of vertices that are above and below, you can use that to generate your index into the marching cubes lookup table. So you end up with this index value, which is just an integer. Here it's in binary, and that's basically how you would access the table. And then you just, once you actually know there's a crossing, you use linear interpolation along the edge to find out exactly where the crossing is. And that's just using the same linear interpolation formula we had 2 lectures ago. And then if you care about lighting, which you almost always do because you have explicit triangle graphics here, you want to compute the normal at each vertex. Well, actually, now that I think about it, there's a few ways you can do this. You could actually you can compute the normal at the vertices of the cell, or you can find a way of computing them at the interpolated edges. You'd probably want to pre-compute them at vertices of the cell, exactly as they're doing here. But there are a few ways of doing this. There's a recent paper called Flying Edges that is clever in terms of how it does this interpolation and how it does the lookups of the voxel values. And it basically gives a over 10-fold speed improvement over marching cubes by being clever about how it does that lookup. And then you have the ambiguous cases. And again, the same rule of thumb as in the 2D case applies. There's no right way to do it, but you have to be consistent. You have to actually determine, all right, we're always going to put the surface along what we consider to be the top or the right, as opposed to just doing it any old way. But even when you do that, you don't always get perfect results in the case of 3D. You can still have cases where you end up having what we refer to in topology as a two-saddle, where you end up having 2 crossings, and no matter how you do it, you're going to end up having a surface that is going to look disconnected, if you've just sort of arbitrarily chosen this is up and this is right. So 2D you only really have to care about up, and in 3D you have to care about up and right. And the paper that solved this problem itself has over 600 cites as of last year, which is also qualifies it in the visualization grades. So it's probably above the Levoy paper on volume rendering in terms of number of cites. Maybe not above the Drubbin paper, but all this is really doing is coming up with a consistent way of resolving the ambiguity in marching cubes. Now I'm going to skip over some of these slides because it might take a while, but the basic idea of this paper called the asymptotic decider is to look at the faces of the cells in marching cubes and look at how your trilinear interpolant turns into what look like a set of hyperbola. And it's going to try to use the asymptotes of these hyperbola. Has a quick show of hands, who's studied conic sections before in geometry class? Yeah, so it's really a very similar principle. You're looking, if you look at a section of a cone, I guess in conic sections it would be quadratics, but in this case you're starting with a cubic, and then you are taking a plane and reducing that to a quadratic. And the idea is that you can use that quadratic, and if it actually is a hyperbola, you can find the asymptotes of that hyperbola, and you can use this to kind of give you an intuition of whether the surface is an innie or an outie. And this kind of doesn't make sense until you see some examples, but the end effect is that you end up dividing your face into something that looks like this. Those crossings are the asymptotes. Then we need to look at the two components of the asymptote, the two quadrants, where there's actually a crossing. And those quadrants actually determine where the triangles go. And the fact that you connect these triangles and not those triangles. And this is a really easy determination to do in 2D along the faces, but impossible to do in 3D looking at the whole voxel. So these are the cases in marching cubes where there's at least one ambiguous face, and the asymptotic decider basically solves that problem. And that's it. That's the asymptotic decider which fixed marching cubes so that you didn't have weird holes when you had certain values at vertices. So to summarize marching cubes, there are 256 cases that are reduced to 15 by symmetry, which was the main, I guess, technical contribution of the Lawrence and Klein paper, even if it wasn't really the first to discover the idea of isocontouring this way. And you have the asymptotic decider that fixes the ambiguity in certain cases, and that's basically it. So here's just a few kind of old-looking examples of isosurfaces. These are very much 90s graphics, so apologies for that. But it gives you an idea. You can apply it to this neg-hip data set, which is, I think, it's a computational chemistry data set. They had an aneurysm, and a scanned lobster from a CT scan. So you can apply it to any sort of volume data set that we've applied volume rendering to, at least structured volume rendering. Yeah, so that this is, I guess before I go on, I should mention the effect of resolution. So conventionally, you would apply marching cubes on the same original resolution that your data set is. So if you have a 512 cube volume data set from a CAT scan, then one voxel is just, one cell is one voxel from that data set. But you also have the option of picking a coarser resolution and interpolating somehow, or doing an additional smoothing filter or even a sharpening filter on that data set, and then doing a coarser resolution marching cubes. The advantage, this is more for back in the day, but the principle still holds. If you have a coarser resolution marching cubes, you get a worse quality mesh, but you have a much faster compute time and much less geometry to actually render also. So that's just sort of an aside. Marching cube variants. So before talking about more exotic variants, I mentioned that there was another paper that came before the Lawrence and Klein marching cubes paper. And this is a paper by Jeff Wivel and Craig McFaders and Brian Wivel, who were really pure computer graphics people. And they were interested in modeling what we call now blobbies. So you see, if you think about back to movies like, what's a good example? The Abyss, and you see like those big reflective CG objects. These came out of a lot of the same basic computer graphics research in blobbies, which are artificial implicits that come from a bunch of points with radial basis functions around them. So the world cared a lot less about this than it did about how to isosurface volume data coming from a CT scan or MRI, but this paper still did it a year earlier. And the only real difference was that it had a 256 case table, and it was looking at sort of synthetic computer graphics data as opposed to real-world visualization data. So another paper, and I think this one is actually really unsung, because marching tetrahedra are probably used in a good 70, maybe 80% at least of use cases I can think of where you actually want to have an isosurface for computation as opposed to volume rendering for visualization. So especially in CAD disciplines where you have a lot of finite elements modeling, a lot of first order finite elements modeling where you have a TET mesh to begin with, you have to figure out how do you get an isosurface out of a TET mesh as opposed to out of a uniform grid. And what's actually interesting is that it's in fact easier to get an isosurface out of a TET mesh than it is to get out of a uniform grid. And you can actually apply the same algorithm to the uniform grid by turning each cell in the uniform grid into either 2 or 8 tetrahedra, depending on how you do it. The challenge is that when you do that, the meshes you get out of this marching tetrahedra algorithm can be really horrible. There are many, many more triangles. So for many years, people thought, oh, we don't really care about marching tetrahedra. But I'd say for multiple reasons, like nowadays, we're talking, 30 years after the marching cubes paper came out, and maybe less than that for marching tetrahedra, but still a long time ago. I'd say marching tets has probably not just made a comeback, but I'd say it's being implemented in some ways more frequently than marching cubes. And a lot of the reason for that is also that it's very easy to parallelize this compared to how easy it is to parallelize marching cubes. But anyway, I'd say both of them are fairly straightforward to implement. And I guess I should mention one last advantage of marching tetrahedra is that in the case of marching cubes, the underlying implicit surfaces, if you look within one cell and you have a trilinear interpolant, those are natively piecewise cubic surfaces. So there's some weird curved geometry that happen to have a C0 discontinuity at a boundary. But marching tetrahedra are always just standard linear. So it's just linear interpolation everywhere using barycentric coordinates. It's very, very easy to handle. And it looks kind of ugly and choppy unless you smooth your normals out, but it's a lot easier to handle. So one thing people noticed early on with marching cubes was that in addition to generating terrible meshes in some cases, it also generated really, really terrible meshes if you had sort of off-kilter geometry or off-axis geometry. So if you have just a cube and you turn that into a volume data set and then you try to find the isosurface of that cube using marching cubes, you'll end up with sort of facet artifacts like this that just generate horrible triangles, look ugly, and really are not what you want to do. And even if you increase the resolution, oh yeah, sorry, did you have a question?
Me?
Oh, no, never mind. Just a slightly uplifted hand. Even if you increase resolution, you can't eliminate these problems entirely. So there are a bunch of people, I mean, there are probably hundreds, if not thousands of papers that are improving on or deriving from marching cubes in some way. But some of the more successful ones that I can think of that came out of sort of the early 2000s SIGGRAPH community, less IEEE Viz, but especially SIGGRAPH in the early 2000s, they were trying to find ways to fix marching cubes. And one of the ways was to use the gradient of the scalar field to sort of replace your vertices and kind of tweak what marching cubes does that way. So it would have some sort of edge detection algorithm, very similar to what you'd have in 2D, but applied to 3D scalar fields, looking at the gradient. Then you'd sample, you did some additional sampling at those features, and then you would sort of correct what your marching cubes is doing by placing samples inside the cube, so placing vertices inside the cube, and then connecting them in sort of sensitive spots. And this greatly improved mesh quality and wasn't a complete revamp of marching cubes. So people really, really like this paper, especially in not so much the visualization community, but especially the CAGD and modeling communities. They really use this sort of technique a lot. Another extension of marching cubes is dual contouring. So here the idea is that if you have volume data sets, not just from modeling techniques, but also from, for example, adaptive mesh refinement, non-uniform grids, hierarchical grids, things like this. Marching cubes can be really inefficient at handling those sorts of data sets. Either you have really high resolution, or and very slow performance, or you just subsample it and you have horrible results. So dual contouring was sort of a way of looking at the dual, putting vertices inside cells of various resolutions and doing marching cubes on this sort of adaptive mesh. And in some ways it was a little bit like, at least the Schaefer and Warren paper that you see on the right was a little bit more like marching tetrahedra in terms of what it was doing, whereas the dual contouring of Hermite data, that's more like sort of a hack on top of marching cubes. But there are these techniques for sort of adaptive marching cubes. So in addition to papers that were fixing marching cubes, there were lots of papers that were sort of analyzing how marching cubes behaved when you actually gave it real data sets. Most of these were coming out of the computational communities, but it's, I'd say this is continued to be a really active area of research. Let's see. Yeah, so this Edge Groups paper is just one example of that. There's also the histograms and isosurface statistics paper. I won't go too much into detail on these, but suffice to say, you have an algorithm that is so popular but limited, and you have an entire research community over the course of 20 years that has basically evolved to solve how to fix problems in marching cubes. So that gives you an idea of how important this algorithm is, not just to visualization, but to graphics and model representation and computing on spatial data in general. So we talked about meshing. So how do we generate a mesh from an implicit isosurface somehow? And now we're going to talk about how you would generate a bunch of particles on that isosurface and use those particles to render or to analyze that surface. So one paper that did this from IEEE Viz 06, from John Schreiner, Carla Scheidegger, and Claudio Silva were also involved in this, is this Advancing Front paper. And this paper really sought to be kind of marching cubes, but better in every way. So instead of just turning your volume data set into a grid, finding the crossings and connecting the dots and getting a surface out of that, what it was trying to do was it was trying to place particles at a specific place where you knew the surface existed and kind of march along the surface, gathering points together, connecting them as you went, and stitching them together and generating a really, really nice homogeneously sampled mesh in the process. So it was incredibly expensive because it was using sort of computational geometry techniques like local feature size, continuous curvature of the scalar field to determine how many points you needed to place where. And it was very slow, very hard to parallelize, but it generated fantastically nice meshes. And of course, you actually had another problem, that is, when you come around to the opposite edge of your isosurface, you actually have to stitch all of your points together, and it took them a really, really long time to solve this. but that's, I'd say Advancing Front is probably one of the best alternatives I know to marching cubes. So there's another paper actually from Mariah Meyer back when she did scientific visualization for her PhD thesis. And this was a particle system for, she was applying it towards sampling of higher order finite elements data. And the idea is you have a contour here, you have some interpolation filter, some interpolation kernel that is incredibly costly to evaluate. And you know it's continuous, but it's much, much more effective to generate samples in some arbitrary reference space and then project them onto world space and sort of sample in a place that's well spaced and homogeneous with respect to the computation, and then do the sampling there and then generate the particles in world space, as opposed to trying to interpolate in world space, which is what you would do in marching cubes or advancing front or any of these other techniques. And this was great because the idea is it's really easy to go from this reference space to world space, not vice versa, but with maybe several thousand particles, you could generate a really, really nice surface, and you only have the question of how do you actually render that surface. So she started off with sort of simple renderings of a bunch of equidistantly spaced particles in reference space, which turned out to be images like this, and then she would sort of add more and more until they coalesced into a surface. And what was nice about this is that you could do this not just for these sort of splatted dots, but also to generate a mesh from it. Once you knew something about how close your particles were together in world space, you could actually turn this into a big mesh, and and that's more or less what she was doing. And she had a paper where she compared the quality of this technique to advancing front, you can see in the center here, and then to original marching cubes, which looks absolutely horrible. And this I would say is the other good alternative to marching cubes, is really a big particle system that's sampled somehow and then turned into a mesh. So along the lines of particles, you don't actually have to generate a mesh from particles, you can actually just render them directly. And this is not really a viz paper, this is more of a graphics paper, but back in SIGGRAPH 2000, they were interested in turning everything into an implicit surface model and just using points to render them. So there were a lot of papers in a community that referred to itself as the splatting community, where they were doing exactly that. So they would sample somewhere in world space, generate a point, project it using just standard rasterization, but there was never any triangle in the surface at all. The idea was that you always had enough points, that your only problem was that you had to filter out the points you didn't care about and somehow make a resulting smooth image, but you never actually had to generate triangles, even if you got really, really close. So there was this Rusinkiewicz and Levoy paper on QSplat that really created this whole field. And then you had a series of papers that really extended this to scientific visualization, spatial visualization, that were looking on how do you do this on something like an aneurysm data set, where it's really, really noisy. Marching cubes generates just triangulated goop. How would you do this in a better way than marching cubes? So there was a technique that was basically similar to QSplat, but had some sort of additional interpolation to get your sample closer to where the actual isosurface was. And then you had sort of papers that were a combination of splatting and marching cubes. So it would be actual marching cubes if you were really, really, really close to your surface and you needed triangles, or really, really, really far away and just wanted some overall representation. What they showed in this paper, and this is Yarden Livnat here at the Ski Institute, and Xavier Tricot, who's now at Purdue, they basically showed that you could get faster performance than most of the ray tracers out there, and run this on just like a Mac. I think they had a MacBook Pro in the mid-2000s is what they were running this on. And these are pretty large data sets. This is the full visible female. And the funny thing is that these techniques were great for the time, but they all, I would say circa 2009 or 2010, they all kind of died, because people realized that they were really, really special case, really tough to reproduce, and there were simpler, more scalable techniques out there, specifically ray casting and ray tracing. And the beautiful thing about the ray casting and ray tracing approaches is that if you have wimpy hardware that's single core or maybe two core, they're going to be very slow. But if you start to have more multi-core hardware and you start to have larger data, the size of the data doesn't really matter very much at all. What really matters are the size of, how much memory you have and can your computer handle it. So really what's happened is that computers now can more or less handle it, either on CPU or GPU. So you have ray tracing and raycasting solutions for direct isosurface rendering that are just more practical today than they were about 10 years ago. So the best one I can think of there is RTRT, which actually came out of Utah in 1998. Steve Parker, now at NVIDIA, came up with the real-time ray tracer, which was implemented on what they called a supercomputer, but is really now just kind of a large multi-core workstation. And they were really the first to render the entire 1 gigabyte visible female data set directly, with no sort of approximations, and being able to really come up with an alternative to marching cubes. And this was, I think this won best paper at IEEE Viz 98. And the magic behind this idea is actually, so in the case of marching cubes, we're turning everything into just piecewise linear triangles, right? But in the case of this ray tracer, what they were doing is they were solving for the analytical intersection between the ray coming from your eye, your viewpoint, and the implicit surface inside this three-dimensional cell, which was piecewise cubic. There was a previous, modeling and geometry person, Schwarze, who came up with a technique for doing this, and Steve Parker adapted the Schwarze technique and put it in, it made it really the centerpiece of the ray isosurface intersection. This was all done in double precision, so it was very wasteful, very costly, but you could do it. And based on that one technique, there were probably 4 or 5 papers that came out of it. I was involved in 3 of them, 4 of them. So there was a time in the mid-2000s when, the ray tracing, it was almost impossible to ray trace or raycast large volume data on the CPU or even on supercomputers and make volume rendering effective. Volume rendering is something you had to do in a GPU, you had to use a slicer for. But if you cared about discrete isosurfaces, maybe multiple discrete isosurfaces, and you had really large data, you could do this really, really fast on a single CPU or on a small workstation. And you could get much better quality than you could get out of even GPUs. But you could also do this technique on GPUs, and I'd say nowadays if you look at the implementation of raycasting isosurfaces or ray tracing isosurfaces and even the Intel software like Osprey, it actually is it's closer to what Marcus Hadwiger was doing in his 2005 Eurographics GPU paper than what I was doing with the Schwarze solver and all of these sort of low-level numerical techniques back in the mid-2000s. And here it's really a lot more like volume rendering. You just take a bunch of samples and you find out where the implicit surface crosses in between your samples. You maybe do a few iterations of Newton or secant, and then you plot your isosurface there. And that's really all of these GPU techniques we're doing. And then in 2009, I had a paper at IEEE Viz that was basically combining volume rendering and isosurfacing. So it would sort of isosurface at the peaks and then volume render every place outside the peaks. And this was great because you had features like these really, really sharp, spiny dendrites, or things that you couldn't easily pick out unless you had a discrete isosurface, and would be really, really slow if you just brute forced volume rendered everywhere with a really high sampling rate. But if you put a peak here in your transfer function and you use sort of a discrete isosurface raycasting technique to find that, and then you just sort of sampled the volume everywhere else, you got really good results really fast. And I'll give you a quick little demo of that, just to give you an idea of what isosurface raycasting looks like. So this is what volume rendering looks like. You can see you're missing a lot of features. I mean, you kind of get a sense of where things are, but you basically have a lot of holes in your volume. And if you want to turn on isosurfacing, so basically the isosurfaces are at the green and red peaks here. Let's see, this is some really old code, by the way. Let's see, peak isosurfaces. And you can see you have to increase the quality a little bit, but you're basically able to get isosurfaces directly out of it. And you can apply higher order filters to it. You can move your ISO value around. And these are things that especially for larger data, would be really, really expensive. Let's see, expensive in using marching cubes or something like that. So yeah, you can sort of see changing the ISO value. And I'd say this is along the lines of more flaky research. In the last 3 years, there's been a lot of interest in what you do not for single field, scalar field data, but multi-field data. And there's been a line of research, mostly from Hamish Carr, Julian Tierney, myself, and a few others, involving fiber surfaces, which are sort of generalizations of ISO values to higher dimensional multi-field data. The idea here is that you are looking at, instead of a 1D histogram to say, I think an isosurface is good here, or there should be a peak and a transfer function here, you're looking at a 2D histogram, and you're annotating that histogram with polylines, with curves, and using these curves to sort of guide what comes out of your multi-field data. And what's interesting about this is, in some ways, it's a lot like the 2D classification that we looked at in the volume rendering lecture, but it actually gives you an even more precise kind of scalpel-like tool with which to determine boundaries. And in addition to determining boundaries, you can use it to sort of summarize large multi-field data sets. So that's, I'd say, more the ongoing research than something that would be implemented in practice tomorrow, but that just gives you an idea. So, isosurfacing versus volume rendering. So advantages of direct volume rendering. You can see the whole data set. You have sort of native filter kernels and per pixel accuracy. It scales really, really well because you can terminate your array when you've actually hit something opaque. It used to be really slow, and not a lot of people used volume rendering because they didn't have access to good implementations of it, but that's really changed in the last several years. So now there are good implementations in ParaView, Vereen, Images 3D, increasingly Visit. And I think what's happened is people are starting to sort of get transfer functions as a result. Advantages of the isosurfacing. Isosurfacing is what you want to use anytime you need to do subsequent analysis or computation from a mesh. It's really kind of your only option then. Triangles are still easy to render, even if you're not rasterizing them. And also, humans tend to think of surfaces. So even if you're not using marching cubes specifically, but you want to visualize a contour or several contours, very often it's easier to understand your data set in terms of 3 or 4 contours than it is to just do a big volume rendering with like a ramp, like a color map ramp, and not really spend time on the transfer function. And yeah, so a lot of these are reasons you would want to go for isosurface raycasting as opposed to marching cubes or direct volume rendering, but there are pros and cons to all of them. It looks like I'm going to run out of time. When is class officially over?
3:20.
3:20. Yeah, okay, so I guess I'll spend 5 more minutes talking about topology, and then everyone can run free. So, topology, this might be a bit of a stretch and a lot to cram into one lecture. But really, the reason we're interested in contours is going back to that simple example with the height field, where we want to learn something about our data set by having relatively few specifications of interesting values or interesting regions of the data. And that's really what a lot of topology is trying to do. The idea is that fields are hard to understand just by rendering them. And by using a 1D transfer function, or even a 2D transfer function, or having isosurfaces in the right place, you're not really getting the whole story out of your data. And topology, a lot of the topological research in visualization is about trying to come up with mathematical tools for decomposing data in ways that don't change when you change the resolution of your data set, or you use a different reconstruction filter, or you just have a change in transfer function or a change in a few contours. So they're trying to learn about how the characteristics of the data, irrespective of discretization, and so really it's about understanding the underlying complexity. And it's really more about learning the continuous properties of the data as opposed to dealing with the limitations of your discrete data. So topology in mathematics studies properties of scalar fields, or actually any fields, which are preserved under continuous transformations. So stretching and bending would be examples of continuous changes. And anytime you have tearing or gluing, like trying to piece a mesh together, adding a vertex, any changes in connectivity are discontinuous changes. In the math classes, who's had a math class involving topology? Okay, it's very similar, except we're dealing with discrete grids at the end of the day. But it's really about the understanding connectivity of these sort of continuous rubber sheet manifolds and really how space is connected. Coming out of the topology math literature, you have these canonical examples of the bridges of Königsberg. You have the Mobius strip, which is a non-oriented manifold. And then you have the coffee mug turning into a donut. These are sort of the quintessential topology examples of something that looks very similar but actually has the same genus, the same number of holes. Same thing with the bridges of Königsberg. And in the case of orientability, it's the idea that you have a surface that kind of flips onto itself, but you're able to represent this mathematically. So what we care about is kind of going back to the height field case. And in the height field, a lot of the time what we're looking at is where's the peak and where's the valley. And we can actually look at this considering just gradient and considering the C0 derivatives of, in this case, a 1D function. So here we would have minima and maxima, the zero derivatives. And these partition the domain into what we consider monotonic regions. So these points, we call these critical points. These are actually fairly useful in decomposing the data. Whereas before, this might be maybe a discretized line with 1,000 bins or 1,000,000 bins. All of a sudden, you're able to chop it up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like 14 critical points. And that more or less summarizes everything your data set's doing. And this holds true in the 2D case when you're looking at contours. What if all of a sudden you didn't have to store your map, you actually just had to store the values of the contours you cared about that were minima or maxima. And the only thing that's different is that in the case of 2D, you end up with something called a saddle. That's sort of a minimum with respect to one direction, or going down in one direction and up in another direction. So yeah, these the local minima and maxima are called critical points. And when you connect these critical points together, that defines the topology of the scalar field, which also gives you a partition of your spatial domain. And what we just showed were 1D and 2D cases, and next time I lecture, I will continue and talk about the 3D cases. Yeah, that's probably a good place to stop. Let's see, so just really fast, I'll go to the last slide and talk, and yeah, so I guess next lecture, the last spatial viz lecture, I'll talk about the remains of topology and vector and tensor field visualization. And hopefully I'll be able to cram everything in. Thank you very much for your attention.